Welcome to deriving the heat equation solution, part A. So first up, recall that we are working, or we are interested in the model first partial with respect to t of u is equal to a squared times the second partial with respect to x of u. This is for t greater than 0 and 0 less than x less than L, with boundary conditions. U of 0t is equal to 0 and u of lt is equal to 0. This is again for t greater than 0. And then with initial conditions, u of x0 is equal to f of x. And this is for 0 less than or equal to x, less than or equal to L. So we are going to perform a trick called separation of variables, which is essentially to separate this into equations with one independent variable instead of two. So this is the goal here with separation of variables, is to separate the problem into two problems with only one independent variable each. So what we are going to do is we are going to assume that u of xt can be written as a function capital X of x times capital T of t. Then we have that the first partial with respect to t is just capital X times t prime. We have the second partial with respect to x of u would be the second derivative of x times t. Again, these are all capital X and t at this point on the right-hand side of our equation. So we get that our partial differential equation becomes x, capital X times capital T prime is equal to a squared times capital X double prime times t. And so we can go ahead and now perform separation of variables. So separating the variables. Again, capital X is a function of x, capital T is a function of t. We get t prime over t. And I'm going to actually move the a squared as well. T prime over a squared t is equal to x double prime over x. The only way for this to hold true for all values of x and t, lowercase x and t, is if these are equal to a constant. So the only way for this to be true for all t greater than 0 and 0 less than x less than L is if these are both equal to a constant. And so we will pick the rather convenient constant of negative lambda. So we are dealing with t prime over a squared t is equal to x double prime over x is equal to negative lambda. We will now split this into two equations. We have an equation in x and an equation in t. So we have an equation in x and an equation in t. Our equation in x, we are looking at x double prime over x is equal to negative lambda. But we can rearrange this. This means that x double prime is equal to negative lambda x, or x double prime plus lambda x is equal to 0. There's a reason why we've been focusing on this particular, or we focused on this particular differential equation when we were doing boundary value problems. It's because it's extremely useful when solving the heat equation. In t, we are looking at t prime over a squared t is equal to negative lambda. So we get that t prime is equal to negative a squared lambda times t, or t prime plus a squared lambda is equal, t prime plus a squared lambda t is equal to 0. If you wanted, we could have left the left-hand side in the separated form, or sorry, the right-hand equation in the separated form, or we can write it in standard linear form. Furthermore, we can also translate our boundary conditions. So our boundary conditions on x we had that u of 0 t was equal to 0 for all t. This means that 0 is equal to x of x times t of t. Sorry, 0 is equal to x of 0 times t of t for all t greater than 0. So in order to have a non-trivial solution, that means that x of 0 must be 0. Okay. So in order to have a non-trivial solution, we have that x of 0 equals 0. Similarly, u of lt equaling 0 translates to x of L is equal to 0. The initial condition does not translate well because the initial condition, we don't have that if we multiply to 0, one of the terms have to be equal to 0. So our initial condition involved t. So our initial condition of u of x0 equaling f of x does not translate into the separated variables. But we essentially wind up with two problems to start off with. So we essentially wind up with two problems. Our first problem is the boundary value problem, x double prime plus lambda x equals 0, with x of 0 equaling x of L, both equaling 0. And our second problem is simply t prime plus a squared lambda t is equal to 0 with no initial or boundary conditions on it. So in the next video, we will solve these two problems and put them back together to find u.